Let's see implementation of optimal binary search tree. As we know that for optimal binary search tree, we have to read number of keys as input, and with number of keys we also need to know the probabilities of successful search and unsuccessful search. So here we include necessary header files, and the maximum number of keys which a tree can have are taken as 10. Then we define a class where name is given as OBST. Now in this class we define some data members. So we know for optimal binary search tree problem we have to calculate weight matrix, then root, and then cost. So these are W, C and R. These are three arrays which are two-dimensional, and we also need to know like what are our keys. So here we have taken input array A, which will hold our keys. P of max is probability of successful search, and here Q of max plus 1 is probability of unsuccessful search. So reason behind this we already know, where probability of unsuccessful search is 1 more than probability of successful search. And then we are going to define some variables which are required during the program. Now in first member function of our class OBST, we are reading the input from the user. So this is accept function which basically accepts the data, input data from the user. So first of all we read how many keys are there. So those keys are stored in N. N is just a count, but actual values of keys will be stored in input array, that is A. So A of 0 will hold first key, A of 1 will hold second key, and so on. So with the keys, we also read their probabilities of successful search and probabilities of unsuccessful search. So we know that we have already seen a problem statement here, where we have seen if I take any problem, probability of successful search, it starts from 1. We can see P of 1 to 4. So P of 1 is actually probability of successful search for key 1. And if I talk about this Q, then it starts from 0. So Q of 0 is 2 here, and so on. So that's what we have to remember while reading the keys as well. So while reading probabilities of successful search, the loop counter variable is set to 1, which goes from 1 less than equal to number of keys. And the probabilities which we are reading for the keys are stored into array called P of I. While reading probabilities of unsuccessful search, the loop counter goes from 0 less than or equal to number of keys, and then we just read the probabilities and we are storing that into Q of I array. So this is exactly same. The accept function reflects the same logic which we have used for reading the keys. Okay, reading the keys with their two probabilities, successful search in P array and unsuccessful search in Q array. Now let's talk about this build OBST function, which is basically driving code for building our optimal binary search tree. Just like we have done while solving the problem theoretically, first we have to calculate cost of each node, and we start with pairs of j and I where difference is 0. So how this value will give me difference at 0? So what we have done here, for I equal to 0, I less than equal to n. Now why it is done? Because if I consider Q of I array, so it starts from 0 and goes till number of keys. Consider if I have 4 keys, then in Q array I will have 5 values, right? So that's why I started from 0 and I less than equal to n, I plus plus. And here W of I equal to Q of I. Now someone may argue that the formula is like W of Ij equal to something. But as here values of I and j are same, so j is easily replaced with I, and that's why it is written as W of I equal to Q of I. We know when this absolute difference is 0, root and cost, these matrices, they will remain 0. Only weight will have exact same value as that of probability of unsuccessful search. So here W of I is simply assigned to Q of I. So that's all about step number 1, where we are just updating the weight by assigning it to probability of unsuccessful search. And now next loop is where we are finding the values of I and j, so that in step 1 it will give us j and I absolute difference as 1. In next step it will give us difference of j and I as 2. In next step it will give us it as 3. In next step it will give us as 4, and so on. So here the loop written is like this. For m equal to 1, m less than equal to n, m plus plus. Inside we have taken another loop, I equal to 0, I less than equal to n minus m, I plus plus. Inside, now we are calculating value of j here, which is basically addition of this I and m, so that every time it will always give me absolute difference as 1, 2, 3 or 4 and so on. Sorry. Next we calculate weight. So W of ij formula already we are knowing. W of ij equal to W of ij minus 1 plus P of j plus Q of j. And for calculating cost, we have to know for which value of k we are getting minimum cost, and then that cost we are assigning as it is to the root. We are finding out for which value of k we are getting minimum cost, and that k value is directly assigned to r of ij. Now for that purpose we have written another function called find on I and j. So find function basically takes two parameters, that is value of I and j. Because we know what are the possible values of k. K should be greater than I, that is I plus 1, and less than equal to j. So here in find function what we have done, we have taken one minimum variable which is assigned to some random value. So for example, I have taken 32,000 here. You can have any value here in minimum. And then inside for loop what we are doing, in inside for we are setting k is equal to I plus 1. So possible range of k is already well known. It should be greater than I but less than or equal to j. And then we check if c of I k minus 1 plus c of kj, if it is less than minimum, then we update minimum with this new minimum value. And yes, that k value for which we have got minimum cost is now assigned to m. So after this for loop is executed, at the end we will have k here in m, for which we have got the minimum cost. And now our task is made much easier here, because this find function is already calculating for which value of k we have got minimum cost, and it is returning that value for us in k variable. So now our task is just to substitute this value of k in our cost formula, and directly that k is assigned to r of ij, because here find function has already identified for which value of k we are getting the minimum cost. Okay, formula of c of ij is same. C of ij equal to c of I k minus 1 plus c of kj plus w of ij, which is recently calculated. So initially when m equal to 1, I will be equal to 0, and how we are calculating j here, j is equal to I plus m. So I will also show you demonstration of this. Okay, fine. Now once these values are calculated, the last thing is to display the contents of optimal binary search tree. Now we know that the search tree, it is a tree data structure, non-linear data structure. So ideally we cannot visualize it the way we are drawing it on the paper. But again, the way is we can use breadth first search using Q data structure to display the nodes of tree level wise. So as our basic focus here is on optimal binary search tree, we are not focusing much on implementation of ADT operation for Q like push and pop. So what we did here is directly we have included this Q as a standard template library, and we are using ready-made functions which are already defined in this Q. So we know at the end when we calculate this cost of nodes, the last one r of ij equal to k becomes a root. So here we know that at the end, like we can see here in this particular matrix, what is this value? I value is 0 here. And what is this j value? J value is 4. What is 4 here? 4 is nothing but our n. So it simply means that at the end, who will be root of our tree? Root of our tree will be r of 0n. And what will be the cost of r of 0n? Cost of r of 0n will be c of 0n. So we display these two things where root is r of 0n and cost is c of 0n. Now, what we have to do? We have to expand this tree. Already we have discussed a formula for expanding this tree. So we can see here, if r of 0n is root, on left hand side there will be r of I k minus 1. So basically I would have to expand this left branch unless I get leaf nodes where both the values in the brackets will be same, and that is how we are doing this by using push and pop function of QSTL. So in the beginning what we do here is we push this first value, that is I value is nothing but 0. So we know the STL has push function for inserting a number in a queue. So initially 0 will be pushed, then n will be pushed. Okay, so now 0 and n is there in a queue. We know now in queue insertion happens at rear and deletion happens at the front end. So next we write a loop while queue is not empty. We are just not taking element out, we are just checking who is there at the front of the queue. So value of queue of front is saved into variable I, and then we are calling queue.pop. So whatever element is there at the front position will be deleted, but as we have saved this value in I, that is available for future reference. And same case we do with j, where q.front is taken out in j and then we call q.pop. So now the second element n is deleted, but yes, we have saved it in j, so that is available for us. Now as per this particular formula, what it says, if I have r of I comma j equal to k as a root, who is there on left hand side? It is r of I k minus 1. So here now what we have done, k is equal to r of ij. So this is what we have done, k is equal to r of ij. Now we have to go to the left subtree. So what we are checking, r of I k minus 1 is not equal to 0. So I have already told you that how many times that this left subtree will be expanded. This will be expanded unless we are getting same values in the bracket. So if they are not equal to 0, it means we have not yet reached to the leaf node level, right? And that's why we want to display that value like C or R of I k minus 1. Okay, and just like we pushed 0 and n and then we popped it out, in very similar way we'll be pushing I and we will push k minus 1 into the queue if this value is not 0. Otherwise, if this is 0, it means there is nothing, and that yes, we have reached to the leaf node level. So there will be dash in this case. So this is about left subtree where we have I comma k minus 1 on the left side. Now what is there on the right hand side? On the right hand side there is r of kj. So here we check, if r of kj is not equal to 0, it means there is a scope to expand this right subtree further, isn't it? Now here we can see r of kj to 4 equal to 4. So 4 is not equal to 0. It means yes, this branch will be further expanded. So again, left side is always what? I comma k minus 1. So that is expanded. And again, right side is what? R of k comma j. So that is expanded, isn't it? So when this r of kj becomes 0, we just come out of this if and we just enter in else, and we show dash there showing that there is no further scope to expand the subtree, isn't it? So this is for right subtree, r of kj is not equal to 0, okay, and this is for left subtree, r of I k minus 1 is not equal to 0. So this is how we can display the nodes in optimal binary search tree level wise. And yes, this is main function where we create object of OBST. We are reading the data by calling accept function, and the core logic of the program lies here in build OPST function. So that is getting called by using object O, and at the end we have O.display, which will display the nodes of tree level wise. We have used Q as a standard template library, which will help us in displaying the contents of the tree. And yes, this program ends here, and it will show you what is root of the tree, what is cost of the tree, and then it will show all the nodes in a tree level wise using Q. Thank you.